Before getting started on looking at the linearity properties of the definite integral, what I want to do is I want to do a very quick review that this set of symbols, the integral from a to b of f of x dx, represents the signed area under the curve y is equal to f of x, and loosely over the interval between a and b. And essentially what I want to be thinking about is that in this kind of notation, the f of x is basically representing the height of this piece of area, and the dx is telling me something about the width of the area. And so just a real quick picture, if I've got an xy coordinate plane like this, and this is y is equal to f of x, and there's a and there is b, basically the height of this particular area, no matter where I draw the line, the height is always going to be f of x, and this dx is indicating that the width is in the x direction. So that dx equal width means that we are integrating in the x direction. So we are integrating in the x direction. Now, what I want to do in this video is I want to look at combining two functions in several different standard algebraic ways. So we're going to let f of x and g of x both be functions that are continuous on the closed interval from a to b. Now, what I want to do is I want to notice that I can create a function that I'm going to call h1 by simply adding the functions f and g together. And h1 is often called the sum of f and g. And it turns out that the graph of h1 has a very nice relationship to the graph of either f of x or g of x. I'm going to think about drawing it with respect to f of x. So if I have an xy coordinate plane, ooh, that should be a y up there. So there's my y-axis. Here's my x-axis. If I have the function y is equal to f of x here, and I graph y is equal to, say, h of x, h1 of x up here, then it turns out that for any particular x, this distance here is g of x. So what I've got is I've got a situation where I can go from the x-axis up to the f of x by looking at going up to f of x, and then I get up to h1 of x by adding g of x that way. Now I'm doing this for every element in the domain between a and b. And so what I want to do is I want to notice that there's a very definite relationship between the integrals of h1 of x, f of x, and g of x. And here's how we're going to build it. I want to actually block in, shade in some areas. So this yellow area, let me actually write that more correctly. This yellow area is nothing more than the integral between a and b of f of x dx. Now I'm going to shade in this red area, and I'm going to talk about that in just a minute. But that red area we're going to think about, and we don't quite know what it is, and I'm going to box in what I'm going to call a white area. And the white area is nothing more than the red area plus the yellow area. So the white area is this. So the white area I can easily see is the integral between a and b of h1 of x dx, and the white area is also clearly equal to the yellow area plus the red area. And the only question is what is that red area going to be equal to? So I want to focus in on that red area in just a little bit more detail. What I want to notice about that red area, and I'm highlighting it as I'm talking about it with this big red arrow, is that the height of that red area is always going to be g of x. And we're sweeping this red area out in the same way that we're sweeping the white area and the yellow area out. In other words, the width of that red area is still a with respect to x and in other words, it's still just a dx. And if I think about what this means, that red area then is going to be the integral between a and b of g of x dx, because this integral represents an area that happens to have height equal to g of x and width go in the x direction. So this particular integral matches up with what we're saying that red area should be. So this red integral, this red area, we can now write it as an integral, is going to be the integral between a and b of g of x dx. And what I now want to do is I want to look at this particular formula and rewrite that formula in terms of these integrals. So this formula right here that we've been talking about can be rewritten as, the white integral is the integral between a and b of h1 of x dx, and that is going to be equal to the yellow integral, which was the integral between a and b of f of x dx. And then we want to add the red area, which is the integral from a to b of g of x dx. And if I think about what this says, I want to also remember, as the very last thing in building a formula, h1 of x was just another name for f of x plus g of x. And so what we get is a formula that says the integral between a and b of f of x plus g of x with respect to x is going to be equal to the integral of f with respect to x, and add to that the definite integral with respect to g. What if we let h2 of x be equal to f of x minus g of x? Then what can we say? So what if we have this thing? Then what is the integral from a to b of h2 of x dx? Well, what I want to do is I want to notice that the equation that we've got up here can be rewritten in a way that we can use our first fact to quickly get a second fact. So what I want to do is I want to notice that h2 of x plus g of x is equal to f of x. And using our first fact, that says the integral from a to b of h2 of x plus g of x dx is going to be equal to the definite integral from a to b of f of x dx. Now, our first property lets us break this integral up, and so we get the integral from a to b of h2 of x dx plus the integral from a to b of g of x dx, will be equal to the integral from a to b of f of x dx. And of course, at this point, it's now an easy task to solve for the integral of h2. This immediately says that the integral from a to b of h2 of x dx is just the integral from a to b of f of x dx minus the integral from a to b of g of x dx. In other words, what we now have is this particular property. Remember, h2 was nothing more than f of x minus g of x, and so the definite integral from a to b of f of x minus g of x dx can be broken up at this minus sign and written as the integral from a to b of f of x dx minus the integral from a to b of g of x dx. Now, if we put this fact together with the first fact, we have what is usually referred to as the first linearity property. And the first linearity property states that if I want to integrate from a to b of f plus or minus g of x dx, I can break the definite integral up at that plus or minus sign into the sum or difference of the two definite integrals. And I do need to write the correct function of that last one. And it's important to realize that you want to think about this formula in terms of English. What it says in English is that if we want the definite integral of a sum or difference of two functions, that it is equal to the sum or difference of the definite integrals of the two functions.